G'day, we're going to talk about Galileo's analysis of projectile motion. And here's Galileo. Now, before Galileo came along, Aristotle's ideas ruled, and Aristotle had the idea of the natural and unnatural motion of objects. So a cannonball fired out of his cannon would follow its unnatural motion path because of the impetus given to it by the cannon. When that impetus runs out, of course, its natural motion will take over and things naturally accelerate towards the centre of the Earth, so it would fall vertically down. Well, apart from being completely wrong, it didn't take too long for people to more carefully observe the path of cannonballs fired out, and they discovered that it actually follows some kind of curved path. But the passion for Galileo was what was the nature of that curved path that this object that is being fired follows. Well, the problem with studying falling motion is it all happens very, very quickly. Now, Galileo lived before video cameras and even stopwatches. So how is he going to make accurate observations, measurements of objects that are falling? Well, he was very, very clever. So what he set up was an inclined plane. Now, the beautiful thing about this inclined plane is that objects will fall more slowly. It's as though he's gone to a planet with a smaller g than Earth and done his experiments where things are slow enough that he can make measurements. But he still had the problem of being able to accurately time things. And what he realised, being a musician himself, is that the human ear is very, very good at keeping an accurate beat. So what he did is he set up these little frets that made a noise as the ball went past them, and he was able to adjust them backwards and forwards, and so that until you got a perfectly even beat as the ball went down. In other words, we got equal time intervals. And once he had that, it was a pretty easy thing to then be able to accurately measure the distance that the ball travels in each of those time intervals. And what results did he get? Well, he got some pretty fascinating results. Over our time intervals, let's say in the first unit of time, it travels 1 unit of distance. In the second unit of time, it travels 3 units, then 5 units, then 7, going up in an even pattern. But what was fascinating, far more exciting for Galileo was when he worked out what the cumulative distance these things had travelled were. So at the end of the first second, it's travelled its 1 unit of distance. The end of the second second, well, it travelled 1 in the first second and 3 new units of distance in the second second. That gives us a total of 4 units of distance. Now in the third second, remember, it's already travelled 4 units, so it's going to add on to that. It's new 5 units, which gives us 9 units, and then 9 plus 7 is 16. Galileo's genius was to recognise, perhaps as you can, what the relationship between these numbers is, and you probably guessed it. It's a squared relationship. So Galileo was able to prove that the distance an object falls is proportional to the square of the time. Now, if you think about that for a moment, what shape does that look like? It's a parabola. The mathematics have already been done by Galileo's time. So Galileo was able to use mathematics, and that in itself was pretty fascinating and quite an innovation in physics. He was able to use mathematics to show something about the real world and to prove that projectiles will follow a parabolic pathway, which is exactly what these dudes at some university are showing as they kick this rugby ball, because it's an unpowered object. It falls into the category of being a projectile, and it doesn't matter whether you kick it up high or kick it sort of down low, it always follows some kind of parabolic pathway. Okay, so let's just have a look at a frame out of that video so we can analyse it, because what we're going to see is the second genius that Galileo brought to his analysis of projectile motion. And that is that the horizontal motion is completely independent of the vertical motion. So what I'm doing here is I'm marking the horizontal distance that this rugby ball has travelled in each of these equal time intervals, each of these certain numbers of frames on the video, something that Galileo didn't have the luxury of. And what we can see here is the distance travelled in each of those equal time intervals is equal. What that tells us is that the initial velocity and the final velocities in a horizontal sense are equal. In other words, the horizontal motion of this ball is unaffected by its vertical motion. But when we have a look at the vertical component of the motion and mark the distance that the ball travels vertically in each of these equal time intervals, we get, again, Galileo's analysis here that that's a squared relationship. The distance travelled is proportional to the square of the time. And that's exactly what happens when we launch a projectile, as this soccer ball shows. So it's now being fired as it rebounds at a certain angle. And it doesn't matter what initial velocity it has, it's always going to follow a parabola. Now, Mythbusters wanted to test whether Galileo was right, whether the horizontal motion is completely independent of vertical motion. So what they did is they set up a truck, you can see it there, with a cannon mounted facing backwards. They organised it so that the velocity of the cannonball being shot out was exactly equal and opposite to the velocity of the car travelling by. And look, there we go. The horizontal motion of the ball is completely independent of its vertical motion. So, in summary, for Galileo's analysis of projectile motion, well, first thing, he used an inclined plane, which was an incredibly smart way of being able to slow things down so that he would make accurate measurements, set up those little frets so he could accurately measure the distance it travels in each time interval. We found that it was a squared relationship between the distance something falls and the time. His other genius was to realise that the horizontal motion is independent of vertical. Now, we're going to use that a lot. When we analyse projectile motion, we're going to be treating the horizontal motion completely separately to the vertical motion and be able to therefore put the two together again and predict the path. And of course, if we put those two together, we find, as Galileo did, that projectiles always follow a parabolic